In this third section of 2.4, we're going to look at something called the rational zero theorem, which will include how to find both the possible rational zeros and the ones that actually are zeros of a polynomial. So the most important thing about this slide, and according to the directions, when I say the possible rational zeros, if you ever see that possible in there, that's going to be the hint that you are just looking for a big long list. Usually there are like 20 to 30 different numbers in here, and that list of numbers comes from the factors of the very last number in the polynomial divided by the factors of the very first number in the polynomial, that first coefficient. So you end up with a list of numbers because for every number you have on top and every number you have on bottom, you combine them into different fractions. And I'll show you this in a couple examples, and then it'll hopefully make more sense. So this is just going to be a list of numbers that might be solutions or might be zeros of the polynomial. And then the second part of the section is going to be which of the numbers out of that list actually are zeros. So once you create your list of factors of the constant and the factors of the leading coefficient, make sure you include both the positive and negative combinations, and then you're going to simplify any of the fractions. So if you pick a number on top and a number on the bottom, like 4/2, make sure you consider that as the number 2. And sometimes you'll see that solutions repeat. You might have 4/2 as one of your combinations, but then later on you might have 8/4 as a combination, which is the same thing. So make sure you don't repeat any of those numbers. So positive and negative versions, simplify your fractions, always simplify your fractions, and you don't have to repeat any of the solutions when you're using this process. So again, I want to stress here that the reason I'm not going through the entire process yet is because this just says the possible rational zeros. Whenever you see possible rational zeros, you'll have the long list of numbers. So in this case, my list, it's going to be plus or minus positive and negative versions. I said the factors of the last number, or the constant, well, 1, 2, and 4 are the numbers that you can multiply together to get 4. And in the bottom, the numbers you can multiply together for the leading coefficient, the very first number, which in this case is a -1 or just 1. That's all that really matters here, because we're already taking into account the positive and negative versions. So the only numbers that multiply together to give you 1 are 1 times 1. So once you have this set up, you're going to create an actual list of numbers by picking one of the numbers on top and one of the numbers on the bottom, and you have to consider every possible combination. So for this case, if I pick 1 on top over 1 on the bottom, that's the number 1. If I pick 2 on top, 1 on the bottom, that's the number 2. And if I pick 4 on top, 1 on the bottom, that's the number 4. So I'm just reducing the 3 possible combinations, 1/1, 2/1, 4/1. I don't see any other ways to pick a number on top and a number on the bottom, so that is my list of possible rational zeros. There are 6 numbers being listed here because I have both the positive and the negative versions. So if they say possible rational zeros, you'll have a list of many numbers, then we'll learn which ones are actually the zeros. Here's another quick example of the list of possible rational zeros. Again, it's positive and negative versions. The factors of the constant are 1, 2, 3, and 6. Those are all the numbers you can multiply together to get 6. My leading number, again, is a 1, so I only have 1 in the bottom, which makes this a lot easier, because that means I just have to worry about 1/1, 2/1, 3/1, and 6/1 as my different answers. So if I reduce those fractions, that's 1, 2, 3, and 6. You will have some other cases where the number out front is not going to be a 1. I'll show you some of those coming up. And that's where you have to start looking at, it basically doubles how many numbers you have to worry about, how many combinations, because then you'll have every number on top over the first number, and every number on top over the second number, and every number on top over the third number. However many numbers you have to cover every single combination. So this is our list of possible rational zeros, and then now we're going to start looking at determining which ones are actually zeros of the function. So please be careful about the difference between when they say the possible rational zeros, or if they just say the rational zeros. So here is the more difficult part of this process, the longer, more time-consuming part. If they just say find the real zeros, not the possible zeros, but finding the real zeros, you're still going to find that list of possible ones first. Then you're going to test numbers from that list one at a time using synthetic division. You're trying to get one that gives you a remainder of 0, or that gives you no remainder, essentially. So keep testing the numbers one at a time until you get one with remainder 0. Once you find one that has a remainder of 0, you can rewrite that polynomial as the factor that you tested times whatever's left under the synthetic division. That's what I mean when I say the product of the quotient. The quotient is what you have underneath your synthetic division, and the root that you found, that's the factor form of whatever you were plugging into synthetic division. So those two things multiplied together, that will break your polynomial down into smaller pieces. Hopefully, at that point, you will just have a trinomial, as in like an x squared plus x plus a number. If that's the case, you can either use the quadratic formula to find the last two answers, or you might be able to keep factoring depending on the numbers. Now, if it is not a trinomial, if what you're left with still has a bigger exponent, if it's like x to the third power or x to the fourth power, then you'll have to repeat this process. You'll have to keep testing numbers until you find another one that works. And eventually, you'll get it down so that all that's left under your synthetic division is an x squared expression. Once you get there, use the quadratic formula or a factoring technique. So first thing I need, since this doesn't say find the list of possible zeros, it says find all the zeros, I still need to list the possible ones though. So my possible zeros, the factors of 6 are 1, 2, 3, and 6. And since all of these numbers are over 1, I can just go ahead and simplify that by saying that's going to be 1, 2, 3, and 6. So these are the numbers that I will be testing with. So basically, you pick one of the numbers, like positive 1, for example. If you plug in 1 using synthetic division, let's see what we get. There's coefficient 1, 2, -5, and -6. So what we're hoping for is a remainder of 0, but we won't know until we go all the way through the process. And I can see right here that this one's not going to work because these two numbers aren't going to cancel out. So that number was incorrect. So then try another number from the list. I tried positive 1, maybe -1 will work. So then I try -1. The coefficients are the same. And I just repeat this process again and again. Now this time it did work because -1 times -6 is 6, and when I add those numbers together I get 0. So in the steps I said look for one that has a remainder of 0, and that's what I just got here. So since -1 is one of the roots that actually worked, that factor would be x plus 1. Because if I took this factor, set it equal to 0 and solved, I would get -1 for an answer. So if -1 is the answer, then x plus 1 is the factor. The sign flips, basically. And then what I have underneath the synthetic division is 1x squared plus 1x minus 6. Now, in the process, I was describing how, look at what you got for your quotient. If this exponent is bigger than a 2, then you have to repeat the process and find another number that works. But since that one worked, now I can stop here and see if this is a factorable expression. So x plus 1 is done. I'm just going to write that again. But I want to see if I can factor x squared plus x minus 6. Well, the first numbers have to be x times x. I want some numbers that multiply to -6 but add up to 1. So I'm going to use +3 and -2. Because 3 times -2 is -6. But if you add the two numbers together, you get +1. So this one was factorable. If it isn't factorable, you will have to use the quadratic formula on it. So my zeros for this polynomial are x equals -3, -1, and +2. And I'm getting that from looking at my factors here, setting them to 0 and solving. This one gave me -3, this one gave me -1, and this one gave me 2. The order doesn't matter. I just think it makes sense to start with the smallest number and then work your way up. Okay, so one more difficult example of this. I'm going to start off by listing my list of possible roots. So my possible roots in this case, the factors of 2 are just 1 and 2. This time I do have a different number out front. So the factors of 3 are 1 and 3. So my possible root, my list of possible roots, now I have to worry about all the different combinations. So I could have 1 over 1, or I could have 1 over 3. So I like to pick one of the numbers on top and then just go through all of the numbers I have in the bottom until I've listed all the combinations. Then I go to the next number on top. I could have 2 over 1, or I could have 2 over 3. So you can see that this list gets much longer, much faster if you have numbers on top and bottom. Luckily, this one only had a couple numbers on top and a couple numbers on bottom, but basically pick a number on top, go through all of the numbers on the bottom, put it over the first one, over the second one, over the third one if there is one, over the fourth one, etc. Then go to the next number on top, put it over the first one, over the second one, over the third one, over the fourth one, etc. So you should end up with a list of lots of possible numbers to test. Now, my recommendation, I usually like to avoid the fraction ones. They're a little bit harder to use synthetic division with. So I like to focus on the regular integer ones first. So in this case, I would be testing +1, -1. If neither of those works, I would go on to +2 or -2. So let's start off with 1 in this case. I'm going to test the number 1 from my list of possible roots, and my coefficients are 3, 4, -5, and -2. The first number comes straight down, and then I multiply, add, multiply, add, multiply, and add. The more you do this, the better you'll get at picking numbers that will work correctly, but for now you probably just want to go through in order and be as systematic as you can with this. So here I got my remainder 0. Since 1 was the solution that worked, that means my factor is x minus 1. I know that because if I set this equal to 0 and solved it, I would get 1 as an answer. From what I have underneath, remember the last number is the remainder, so don't worry about that one. So if this is the remainder, this is the constant, this is x squared. So that means I have 3x squared plus 7x plus 2 for my quotient. And then you want to see if you can either factor this. If you don't feel like you can factor it, just use the quadratic formula to get the other answers. But in this case, I do think this one's factorable. So I'm going to set up my 2 sets of parentheses. First numbers will have to be 3x times x. The last numbers will have to be 1 times 2 to give me 2. Specifically, I'm going to put the 2 here and the 1 here because now my outside product is 6x and my inside product is 1x. 6 plus 1 equals 7, and that's what I needed. So these are my 3 factors, which means my solutions, the solution here is 1, the solution here is -1/3, and the solution here is -2. So you're just going to list those out. I have -2, -1/3, and +1. Now again, I want to emphasize that the reason I knew to actually go through the list of roots and find the ones that actually work is because this did not just say find the possible rational zeros. If they say find the zeros, you need to find which ones actually work. If they have the word possible in the question, then you can stop after you just create the list of ones that might work. The problem is some of these do and some of these don't. So we've narrowed it down from being any number imaginable, but it's not as useful as actually saying which ones do work. So please be careful about that on the directions for which one they're asking you for in the assignment. And we'll practice this more in the next section as well because it can be a difficult concept, especially when we add some more complicated versions.